Recording is about to start. Yep. Hey, cool. And share the screen. Start broadcast. And if everything goes well, you should see the screen. Can you see the screen? Yes. Fantastic. God, we are good. I'm so pleased with myself. How can I live with myself? I'm so good. It's amazing. Yeah, totally expert. I'm fully aware of that. God, Klapper is talking shite. And at least somebody finds it amusing. Yeah, it's the suffering from success. Well, actually, what success? Not entirely sure. And then the next question would be, what do you define by success? What does success look like? I mean, at the moment, I think success is if you are still alive and can join the session. Not being in student debt. Uh, well, let me put it this way. You will get into different forms of debt. So mortgage, etc., etc. And then when you've got kids, they are like parasites. I didn't say that, okay? Oh, is that a horse? Who is galloping? No, I better not comment on that. But please, can you make sure that you have muted? Because otherwise I go totally bonkers. And that's not something that my wife, my kids, or the doggos would very much appreciate. Okay, shall we get started? And again, Bernardo has very kindly posted the link on Moodle for the attendance. And yep, thank you very much again. And I think a very big round of applause for that beautiful duck face. This time I recognize what it is. Okay, so let's start with opening pretty much a new chapter for the BI 308 Skills for Bioscientists module. What we have done so far is we have looked into various things, how we do experiments. So we've calculated molarities, we've calculated solutions, we strayed into the area of pH and buffers. And please don't forget to do the practical. And the link on that to that is on Moodle, but also in the group chat and so on and so forth. And the deadline for the practical is, well, I haven't set a deadline, but I really want you to do it sooner than later because then it's out of the way. We have even looked at spectrophotometry, and we looked at, yeah, that's the practical from Monday, exactly. And we've even looked at how fast reactions actually work and how fast they run, which will come in quite handy when, thank you very much, that's the link. When we are looking at more detailed reaction for those of you who are doing the BI301 enzymes and metabolism module. So we have done the experiments, and now the big thing is, thank you. Now the big thing is, we've got our experiment done, and now we have to make sense of the data. We need to do proper data analysis, because that is what we do as scientists. And the data analysis is there to make sure that, firstly, we understand what the experiments tell us, and also to make, in a way, predictions. If I do this and if I do that, then this will be the outcome. Now, the next question is, let's see, does that actually work like that? And that is really the scientific method, isn't it? That we do an experiment, we want to learn from this experiment. We don't do the experiment just because Clapper says it, or that's what it says in the module outline, etc., etc. We want to gain information about the world, and therefore we need to very critically analyze what the experiment that we just did, what does it tell us? If you are involved in research, what you will find very, very, very often is that you ask a simple question. So, for example, what is the color? Is it, or it's not a color, is it black or is it white? And the answer that you get from the experiment is 11. So you think, what the fluff is this? What does that? I don't understand it. And that already tells you that maybe the question that you asked at the beginning was not exactly right. But nevertheless, whatever experiment you do, you always need to do proper data analysis. And I thought in this first session today, I give you a few concepts that we will need to work with when we are actually looking at the data and trying to make sense of the data. So we have already last term discussed a little bit the concept of sample and population. So that's firstly, that's that's the wrong color. We already discussed these concepts, sample versus population. And I think the easiest way to explain things at the moment is just to do a little experiment that we can use to really illustrate these different concepts that I want you to be familiar with. So let's say I want to know the length of the index finger of all the people on the left hand of all the people in the UK. So that would be my population here. So length of left hand index finger. And as I said, if I, for whatever reason, maybe I want to, produce gloves or something like that. And of course, I would not measure all these index fingers. of the entire population in the UK, so about 60 million or something like that, what I would do is I just simply take a sample, and the sample needs to be representative. And this sample actually would be characterized by, let's say, I ask 5 students, so it would be characterized by the number of observations, so that's n, that's the number of observations. And I would also measure the mean, the sample mean of all these 5 people. Excuse me. And sorry. And I would also measure the spread, and for the spread I would measure the standard deviation. And in this case, because it's a sample, I would measure the sample standard deviation. And we have done that before. Sample standard deviation. And I showed you how we can easily do that. And from these 3, what is called sample statistics, I then will make an educated guess about the population parameters. The population parameters, which we said would be the mean of the population, so that's the population mean. Will I have an n for the population? No, because in this case, I really don't care whether it's 60 million or 60 million and 1 person or something like that. The population is just simply all of it. And I can do the population standard deviation to look at the spread. Population standard deviation, and I abbreviate that with this sigma, to look at the spread in the length of the index fingers. And this process is actually called inferential statistics, because I make an inference, I make an educated guess from my sample statistics to the population parameters. So far, so good. Sometimes, or very often actually in sciences, we will find that our population potentially is very, very large. Actually, it might be that a population can be infinite. How that? Well, if I say, for example, I spread some bacteria on a plate and grow colonies on this plate, something like that, then this surely is a sample, in this case with 1, 2, 3, 4, 5 counts, of all the potential plates, that I could generate in this experiment. How many plates can I generate in this experiment? What do you think? How many plates can I do? Unlimited. Infinite, absolutely. So in a way, my population in this case, as long as I have the resources, I can do plates. It's terribly boring, but I can do an almost infinite number, and in this case, the population would be infinite. So, but still, this one plate is truly a sample of this infinite population. And of course, I can say, right, from this sample, I can calculate the number of colonies and then make an inference or in other words, an educated guess on how many colonies I would expect on average in this population. And how we are going to do that, I will actually show you in the, I think we have a session tomorrow for BI 308. So I will show you how we can actually do this with count data. Now, coming back to the example where we don't have necessarily an infinite number of potential observations, let's go back to the index finger example. So I can ask 5 students, so n equals 5, and I can ask them to measure their index finger of the left hand. And I get a sample mean and I get a standard deviation. These are my statistics. So the parameters characterize the population. The parameters tell me that on average, if I did this experiment, whatever the experiment is, if I did this experiment 1,000,000 times, the true population mean of the colonies would be 10 colonies per plate. And this is a very general and generalized statement. This is what I want to have at the end of the day. I'm not so much bothered about the sample. I want to know what is the length of all the index fingers in the UK, in the world, in the galaxy, for example. Does that make sense? So here is my sample of the index fingers or the length. And again, I can try to use that to make an inference for the population parameters. How long is an index finger? Now, I can say, right, one sample maybe not terribly good, especially if I've got only 5 observations. I want to do better. I've got 2 options now. I can say, okay, I want another sample of 5 observations. N equals 5. That's another sample. And we would probably get, let's call this sample 2. So that's mean 2 and a standard deviation 2. Whereas this one here, that is sample. So that's sample 2. That's sample 1. And we said we have a sample mean 1 and a standard deviation 1. So we have these, and again, I can use this sample 2 to make this inference, to make this educated guess, and find out what is the population. What is my population here? That's my population of all the index fingers. That's absolutely right. We use sample, just a slightly terminology alert. We use sample statistics to guess the population parameters. So when we are talking about sample, it is a statistics. When we're talking about exactly the same thing, about a population, then it is parameters. So now, if I use exactly the same students, so I ask five students to do this measurement, and then I ask exactly, I can ask same students again to repeat the measurement. Repeat the measurement. What purpose could this have? That I ask five students and then I ask the same students to repeat the measurement, say 10 minutes afterwards. What purpose could this experiment have if I did it like that? Accuracy, yes. Reproducibility, yeah, that's very good. I like that, yes. It is reproducibility. It basically tests whether if we repeat the same result, we get a very similar, if we repeat the same experiment under the same condition with the same individuals, with the same measurement, we should get almost the same result. So we test repeatability, or the same word, reproducibility. And if we use the same individuals, this would be called a technical replicate. This is a technical replicate because I check that if we do the same thing under the same conditions, with the same tools, with the same subjects in this case, whether we get the same result. Do you expect, actually, when we do a technical replicate, do you expect that we get exactly the same result? No? No, I think I would agree. It's the same samples. They would not probably be exactly the same to the 150th decimal point. Not the same, but they should be pretty close. So technical replicates, they test if the experiment, if the experimental mental conditions are valid. Conditions are, let's say, valid, and if the experiment is can be repeated. So that gives us some confidence. If we do the same thing, we get the same result. And it could be a little bit of human error. It could be, God knows what, but it should be pretty similar. So that's the technical replicate. What's the opposite of a technical replicate? Does anyone know? No? It's not a control. An untechnical. I like that. The correct term is actually a biological replicate. And a biological replicate is, in this case, I ask 5 other students. So, as I said, we have a sample here, n equals 5, x bar and s, sample 1. And I've got sample 2. Let's make it easy. N equals 5, x bar 2, and the spread S2. So, and in this case, the students are not the same. So they are biologically different. What do I expect? What do I expect my sample means? Would I expect that the sample means are the same that I get when I do this measurement? No, absolutely right. Should they be similar? Well, actually, they will most likely be similar. Now, if these two samples actually come from the same population, the way I have drawn it here, I expect difference, expect a difference. But this difference is really only due to what? What is this difference due? The difference between sample 1 and sample 2. Individuality, yes. What's the technical term? What is this difference due to? Variations, yeah. What else? We've discussed that. There is a technical term for that. Samples are different due to sampling due to sampling due to sampling due to sampling error. Yes, thank you. Sampling error. Whenever we take a sample, it will be different from another biological replicate, just simply because due to this thing, sampling error. We will all, when we work with samples, they will never be really the same because we have individual differences in there, and these individual differences will actually change the mean. So if I ask 5 different students for the length of their index finger, we will see that the mean of that sample will be slightly different. It's not a technical replicate because I don't use the same students. In this case, I use a different group of students. They hopefully have index fingers that I can measure. But the mean for sample 1 will not be the same as the mean for sample 2. And this is just simply due to sampling error. And error is a really nasty word. It doesn't mean that we do anything wrong here. It just means that when we use a sample, when we gather samples, it just means that there is an inherent uncertainty in it. So here is, this indicates that it is sampling, I probably should call it sampling uncertainty. Okay, so far so good. Now, what I can do is, of course, I can compare two samples. So again, I can compare my sample here, sample 1 and sample 2. So I have, let's do n equals 5, x bar 1, s1, n equals 5, x bar 2, s2. So sampling error is just simply an uncertainty. Whenever I work with a sample, it will be different from another sample that I take. And that is the sampling error. So as I said, I can now say, right, I've got two samples here. They are different. S1 and S2 are different from each other. I know that. It must be the case because of sampling error. They must be different. Or I expect them to be different. I don't expect them to be the same. They should be different just due to sampling error. But how can I now make a statement? You know, I've got the mean of index fingers from this group of students, and I've got the mean of the index fingers of another group of students. Is there a difference between these groups? And so we need to come up with an idea of how can we compare two samples with each other when we already know that there is a difference. How can we do that? Actually, what we can do is we can say, right, let's just simply look at the means like that and say, let's form the difference of the means. So what is the difference of the means between these two samples? And instead of working with the samples itself, we just now say we are working with the difference of the means here. Difference of the means. Yeah. So instead of with the samples, we are working with the difference. And if the difference is really big, then we say, oh, cool, there is something going on. If the difference is small, then we say maybe this is due to sampling error. Does that make sense? So if the difference is large, then we just simply say, right, there is something going on that we can't just simply explain with the sampling error. But if the difference is small, so if difference is small, this could be explained by sampling error. If the difference is large, then we still have a sampling error, but we also have probably another effect plus additional effect. So in our case, it could very well be that we looked at a sample of index fingers that by accident was taken from some toddlers. So you compare toddlers with adults, and you will find that the two samples are different. The difference is big, and you no longer can explain this difference just by the sampling error. You know that there is actually an additional effect there. There must be an additional effect. We can also actually rephrase this. If we only have the sampling error, if the difference, if this one is the case, there is a very good chance that the two samples come from the same population. Same population. Only the sampling error. Or we can say both samples represent the same population. Or we can also argue that sample 1 is a population and sample 2 also represents a population. So that's population 2. And if the difference is small, we can say we cannot tell the difference between population 1 and population 2. We can tell the difference between sample 1 and sample 2. That's easy. We can tell that. But we can't tell. Oh, let me try to illustrate that better. we cannot tell the difference between population 1 and population 2. If the difference between the samples is small, we don't know whether whether the two populations are different or whether they are even the same. If the difference is large, then we can use it, then we can see it like that. This here is population 1, and this here is population 2. And what we do is, again, we compare the sample means. We compare the sample means and say, wow, that is a big difference, which we can't just simply explain with the sampling error. And therefore, so we say it's a big difference. And therefore, we need to say there is more than just the sampling error. Actually, the difference is so big that we believe the two samples represent two different populations. Two samples represent different populations. And you've seen I'm writing a lot of stuff. So therefore, there is something that we can do, because I hate writing, you hate writing. There is a way to write this much, much faster and more concise. There is sort of a shorthand there. And this shorthand just simply says, we take our two samples, S1 and S2, and from these two samples, we figure out the population mean. So we figure out the population mean, because each population has a mean, and we try to make this inference here. E missing, the educated guess from our sample. I should probably write it like that, because that gets confused with the standard deviation. So we take our sample mean. Let's write it like that. The sample mean, from the sample mean, we make an inference to the population mean. And if we want to say that we believe the difference is small, if the difference is small, we just simply say our two population means are the same. So that would be one hypothesis. The population mean of the two populations that our sample are taken from is the same. Or in other words, there is no difference between the two populations, the difference between the two samples can be explained just by the sampling error. That's one case, and we would write this as H naught mu1 equals mu2. This is the shorthand for this statement here. There is no difference between the two populations. No difference. The means are exactly the same. The difference between the observed two samples can readily explained just by the sampling error. Does that make sense? And if you wonder why it is called H0 or H naught, H stands for hypothesis. And here we have a statistical hypothesis. It's not a sort of scientific hypothesis where I say, oh, I think probably the virus infections are correlated with blood groups or something like that. This would be a scientific hypothesis. This is a statistical hypothesis. This is also called the null hypothesis. Null hypothesis. Because there is a null, and if you wonder why it's null, you can also write this null hypothesis as mu1 minus mu2 equals 0. That basically means the population means are the same. Because if I subtract one thing from the same thing from another, which is the same, I would get 0. So these are two different versions of the null hypothesis. For the null hypothesis, we are comparing the population means. Ah, brilliant. That's an excellent question. What is considered a large or a small difference? Wonderful. I'll come back to that in a minute. Because what we need to do is also, we need to say, well, what happens if the difference is large? We would write this as what is called the alternative hypothesis. The easiest way of writing the alternative hypothesis is the two population means are not the same. Or I can also write this as H1 mu1 minus mu2 is not the same as 0. So both of these are the same thing for the null hypothesis. These are both the same ways of writing what is called the alternative hypothesis. So it's the alternative hypothesis. There are also some slight variations of the alternative hypothesis, but we are not worrying about that at the moment. So the alternative hypothesis is there is a difference between the populations, the two populations, and the difference between the two samples is due to sampling error. Of course, sampling error is like herpes. You always have it. You can't get rid of it. Is due to sampling error plus an additional effect, additional factor or effect. That is what the alternative hypothesis says. And it's exactly the same thing. And what the really nice thing is we always have the same wording. We always have the same mathematical expression here, where we always have something like this. H naught is the same, or the difference is 0, whereas for the alternative hypothesis, we always have it's not the same, or the difference is not equal to 0. If the small difference between the populations, then we can't really tell whether there are two different populations. They could come from different populations, but we would not necessarily see it that they come from different populations. I would say sampling error. If we have a large difference, we can tell, yes, they come from two different populations. If we have a very small difference between the two population means, then we can say it is probably due just to sampling error, but we can't totally exclude that just, by sheer coincidence, they are still two separate, but we can't see that difference, right? So what I want you to take from that, and we are coming to this question, Mohammed, we are coming to that question tomorrow. When are they used? No, we would, when we look at two samples, we compare them, compare two samples. We compare the two samples that we have. And what we do is, before we do anything else, we set up our null hypothesis. We say the null hypothesis, when we compare these two samples, null hypothesis mu1 equals mu2, or you can exactly the same thing is expressed with this other way of writing the null hypothesis, mu1 minus mu2 equals 0. It's exactly the same. So we set up the null hypothesis and we state our alternative hypothesis. mu1 is not the same as mu2, or we can also write this as h1 equals mu1 minus mu2 is not the same as 0. So if you want to compare two samples, and Abigail makes a suggestion to use a t-test, and I will show you tomorrow that this is only partially true. What we want to do to compare the two samples is we need a statistical test. We need a statistical test to make this comparison between the two samples, and then to say, yes, we believe this is true. If we have evidence that the null hypothesis is true, then we can say, no, not this one. Or it could very well be that we say, oh, we have evidence that the alternative hypothesis is true, and therefore the null hypothesis can't be true. And what kind of statistical test we can use, you know what's coming, right? The usual cliffhanger. I shall see you tomorrow. Have a lovely afternoon, and don't forget to do the pH practical. Thank you for watching. Take care. Bye-bye.